Hi, Nitin. I've made you the host, so you can start the class whenever you're ready.
Yeah, ma'am, thank you. Okay, good evening. We'll start over the class. Okay, so starting with the wave nature, again, same thing. We'll just go with the formulas and then start doing the questions. Okay, these are the minimum formulas which is required for solving the questions. We're just revising it off. So any particle which has studied in atomic structure, any particle which is that can have a motion, it can have like a wave as well. particle nature and wave nature both is there. Particle nature, everything is discussed when you're studying about electromagnetic waves. Okay, now wavelength of a particle is lambda is equal to h by mv, which is h by p. Now this ek is kinetic energy. How you get this? If we know that E kinetic energy is half mv square. So if I want to convert it into terms of what? Linear momentum, so we can write this as this. Now this side you can see it becomes half m square v square. So I can write that half mv square is basically nothing but p square. So I can write p square is equal to 2 MEK, and this basically is root over 2 MEK. 2 MEK. So now 2 MEK is H2 MEK. So P is equal to mv and Ek is kinetic energy. For an electron which is accelerated through v volts, any electron which is accelerated with v volt, we write. Normally when a charge is accelerated with any volt, we write the energy for that in the form of Q times V, where Q is your charge and V is the potential. If this is basically when I'm talking about energy, when I'm talking about a force, this is basically your energy. Energy for a particle or for a charged particle which is accelerated to a velocity to a potential v. If we are writing out force for the same condition, we write it as into q into E, where this E represents electric field. So for electron, we can write it as H2MeV. You have a final value to remember is 12.27 root over V. V is potential here, volts. This is in Armstrong. Or I can write this as 150 of whole V. Or total things is in the terms of root. So any one formula you can remember. For proton, this is what is the final value. And for alpha particle, this is what is the final value. We generally have this three related particle only. For an electron revolving in nth orbit of Bohr's hydrogen atom, this is known as what? This is orbital angular momentum, which is integral multiple of h by 2 pi. So we write it as mvr is equal to nh by 2 pi. Since lambda is equal to h by mv, I can write it as 2 pi rn. Okay, this is the formula. Correct. This is mvr is equal to nh by 2 pi. And I have a formula where we write as lambda is equal to h by mv. So if I'm trying to rearrange this, I can write this in this format. How I can write this as I have 2 pi v. I will try to keep 2 pi r over here, and I write it as nh by mv, where h by mv is lambda. So I can write 2 pi r is equal to n lambda. This also sometimes you use. That's what you can write it here, 2 pi r. This is what is the relation. Okay, using both the things, Broglie wavelength as well as the nature of angular momentum. Okay, this is another experiment, X-ray experiment. As what is there is X-ray was discovered by German physicist W.C. Roentgen in 1895. What was done is, when an highly energetic electrons are made to strike on a metal target, electromagnetic radiations come out. A large part of this radiation has a wavelength in the order of 1 angstrom, and this is known as X-ray. This normal experiment, what is there here? You have induction, glass chamber. Why we keep to maintain the we are trying to maintain a low pressure and high temperature so that we will get a condition of vacuum. What is important for you in this, the graph things we are supposed to know, and the few summarized point of this thing is, this is variation in terms of, so we have intensity over here, you have lambda minimum here. These are two constants, we have k alpha and k beta. We'll see what is them. At certain sharply defined wavelength, okay, there will be some wavelength over here. The intensity of X-rays are very large, which is marked as k alpha and k beta. These are known as characteristic X-rays. at other wavelengths, intensities varies continuously. You can see that it is not constant. So these are known as continuous X-ray. So there's 2 points where you have an high peak, you can see variation, you can see that is known as characteristic X-ray. And where you have, there is no variation, it is continuous. So we say it as continuous X-ray. The minimum wavelength for, or the cutoff wavelength for, or threshold wavelength for a continuous X-ray, to have a continuous X-ray, this is what is that. This also will be used in for when we are solving the numerical. This is Hc by Ev, where E is the charge on the electron, and V is obviously the potential volt. So you remember either any value. H is basically Planck's constant, which is 6.62 to 10 to minus 30 for the value for this in SI units. The minimum wavelength does not depend on the material of target. It depends only on the accelerating potential. So you can see the minimum wavelength, which is this lambda minimum. It only depends on, you can see this is the H, C, E, all are constant. Only V is what is changing. H is in Planck's constant. This is speed of light, and this is an electron charge, which is 1.6 into 10 to minus 90. So it only depends, and how it depends is basically we write it as lambda minimum, which is inversely proportional to the volts. Okay, this is how it is related. Next, the continuous X-rays are due to continuous loss of energy of electrons striking the target through successive collisions. So collisions are happening because of that, energy losses are happening. So because of that, you get this thing. You have to know what is for continuous spectrum or the continuous X-ray thing. We try to find out lambda minimum, which is minimum wavelength that is required for the continuous X-ray to happen. That is your Hc by Ev, where you can remember Hc by Ev, or you can remember it as 12,400 Armstrong upon V volts. Okay, 2 peaks will be there. Those are characteristics X-ray. Based on that, you decide about the characteristics of that trace. Okay. Photoelectric effect. What happens in photoelectric effect? Photoelectric effect, basically what happens, we have a surface which we take mostly metal or someone which can conduct, and you allow a light to fall on it. A light will have some wavelength that will be, will try to keep it as monochromatic wavelength. That means it will be a single wavelength. It can be any light. Okay, so this will have an energy of h nu. This is basically energy of a photon, and with that energy it will fall on the metal surface. If this particular surface have a smallest value for which ejection cannot happen if it is lesser than that, so that value is known as h nu naught. H nu naught is nothing but it is known as work function. This is known as work function. This is the minimum amount of energy which is required for ejection of an electron, or you basically we say them as photoelectrons because this is ejected after this light falls on the metal surface. So we say that this is photoelectron, and they move with some velocity. So we can find out the kinetic energy for them because they'll have some velocity after this. So this is known as work function. And mu naught is what? Mu naught is basically your mu naught is basically a threshold frequency. The threshold frequency is minimum amount of frequency which is required for ejection of an electron from the metal surface or from the conductor surface. If it is lesser than that, there will be no ejection. So basically work function is defined as multiplication of h nu naught. Again, I can write this thing in the form of hc lambda naught, where lambda naught is what? Lambda naught is threshold wavelength. I can write h nu also as hc lambda naught. So basically what I'm saying is, for an energy of, if there is a photon with an energy h nu, so there will be ejection only if it crosses the value h nu. So after h nu naught, that is minimum work function, and it is different for different materials. And if that ejection happens and still some energy is left, that particular electron will move within some velocity, which, because the velocity will be there, it is basically kinetic energy. So I can say what is h nu, that is energy of photon, will be utilized to overcome the work function, and if it is able to overcome the work function, it will give some, it will impart some kind of energy in terms of kinetic energy to that photoelectron for the movement. So this is what is known as photoelectric effect. So this in total is photoelectric effect. We have a setup for this. So for what basically happens here is this only. The energy from photon is actually falls on the metal surface or conductor surface. If it is able to that particular wavelength have a certain frequency which is more than their threshold frequency, then there will be ejection of electron. And if still the energy is more, it will provide some velocity to that particularly photoelectron, and that photoelectron can move with an velocity v. As it is moving, it will be termed as kinetic energy. Okay, this is what is. So you can see there is a few points in this. Stopping potential is there, that smallest magnitude of anode potential which just stops the photo current is called stopping potential. We'll see the graphs related to that next slide. Now what is basically the stopping potential? There will be, now see, we said what is, there will be a motion, there will be ejection of electron. So ejection of electron, what I'm doing, I'm trying to connect this electron to this thing, and this is what I'm trying to generate electricity through it. So this is basically I'm trying to generate electricity through photo electrons. So if I want to stop that, there will be the minimum amount of potential which is required to stop that. That is known as stopping potential. Okay. So stopping potential is basically given as EV naught. Okay. So where V naught is what? Stopping potential. EV naught is equal to KE maximum. Okay. So because ejection, I don't want it to go. I don't want the electrons to move. So what I'll do, how much amount of this is there, I'll just in ultra direction, I'll apply that much energy in reverse direction. So what will happen, this will stop. This will, there will be like, it will hit it, but there will be no ejection, there will be no movement of electron. Ejection will happen, but there will be no movement of electron. Kinetic energy of photoelectrons varies from 0 to kinetic energy maximum. Okay, if nu is greater than nu naught is the frequency of incident photon, h nu naught is the work function, then h nu minus h nu naught is equal to Ke max, okay? Maximum kinetic energy. This is basically what is your photoelectric effect. So this is a few graphs which is related to your photoelectric effect. Okay. Now when I'm talking about Rutherford experiment, okay, Rutherford atomic model. 1 second. 1, 2. To do this, you should know this. Okay. So basically to do this thing, what is required is, you can see there is a graph between stopping potential and there is a graph between frequency. You see the metal one is there, it have a stopping potential here. V naught is the second metal atomic potential. Here the stopping potential is this thing. You see you have increased the frequency. So value of stopping potential, any changes are happening. See here the stopping potential was here, and here the stopping potential is still here. So you can see that there's no change on stopping potential when there's any change in frequency. Though I'm taking, okay, now nu naught is there, which is there, correct. Now, but if I'm talking about here, this is what now, this is photo current, and this is I2 and I1 is what? This I1 and I2 are what? Intensity. Now you can see that because of now intensity point, you see intensity 2, I2, I1, only they I2, I1 is going to affect only the photo current. Stopping potential is it changing? No. Stopping potential in the both the case it is same. I'm not changing it. This is stopping potential. You can say it as retarding potential or stopping potential. So when I'm changing I'm increasing the intensity, photo current or ejection of photoelectrons can vary. More photoelectrons will get ejected. So intensity, if higher is the intensity, it will have what? More ejection. So I2 is greater, so more ejection of photocurrent will have more ejection of photoelectrons, so more production of photocurrent. See, same situation. Again, if I'm trying to change stopping potential, there's no effect on this thing. It will still stays constant, the photocurrent. And intensity and photocurrent are proportional directly. How much you increase intensity, that much will be photocurrent increasing. Okay. So this is what this graph signifies. Graphical questions somewhere that are important. Rutherford experiment, we all know a Rutherford experiment, Goldfall experiment. See, the motive of seeing this is not about this. The only thing is what you're supposed to know about this is drawback of this. Now, a drawback of this was what is Rutherford had said what is he explained that the electrons are moving in the circular orbit around some positively charged thing which is containing neutron and proton, and it is moving around that nucleus in a circular orbit. But if because electron is a charged particle, so according to Maxwell law of electrothermodynamics, he said what is if any charged particle is there, so if it is in motion, so now it is accelerated, right? So because it is accelerated because it is changing its direction continuously. Something to be having a non accelerated motion, it should be uniform and should not be changing the direction. Even though it is uniform, but it is changing, the electron is changing direction continuously, so it is said as an accelerated motion. So according to Maxwell, if there is an accelerated particle, we have an accelerated, the first thing is accelerated, and we have a charged particle. So if accelerated charged particle, it is moving, let it be any particular orbit, or it can be straight path or any path. If there is any charged particle which is moving with some velocity, it is having some acceleration. So what will happen is it will keep on losing its energy in the form of electromagnetic radiations. So if it is losing its energy, according to Maxwell calculation, in 10 raised to minus 8 second, this electron should fall into the nucleus, but that was not happening. It was not explained by Maxwell. This was the drawback of Maxwell. He could explain most of the things, but he could not explain this major region. Because of this only, we come up with this thing that we have Bohr's atomic model. Now, what one point here is what? Correct. Most alpha particles went straight. 1 in 8,000 deflected by an angle of 90 degree, more than 90. Atom has lot of empty space. Okay, you need to know about this thing, impact parameter. Impact parameter is given as B is equal to 1 by 4 pi epsilon naught ZE square. ZE square basically stands for ZE into E, where ZE stands for number of charge in the nucleus. So number of proton, whatever will be your atomic number times electron, and this stands for 1 electron. Cot theta 2, this is the angle. This is now basically what happens is this particular electron is coming. So this is an alpha particle. So obviously I'll show the charge is 2 electron. It is coming nearer to the nucleus, and after coming to this position, starts going away. It is not able to come to trace this straight line. So this is why this is happening here. So to understand what happened here, there should be some positive charge present here. That's why this positive charge is getting repelled and it is taking this. So because of this repulsion, it is not able to take this path. So what is the theta here? The actual path is this one, and this is the traced path. So the difference with that angle between these two is taken as theta. Half mv square is kinetic energy. So this is what is our impact parameter B, kZe cot theta by 2 half mv square. This can also be said as your distance of closest approach. This is maximum a particular alpha particle can get closer to the nucleus. Okay. We have the equations for the fraction of alpha particles scattered at particular angle theta. How many of them are scattering? So n theta is equal to proportional to z square, or n theta is proportional to sine the power 4 theta by 2. Distance of closest approach, maximum how much nearer the particular alpha particle can reach to the nucleus. So kinetic energy, where it will be that position where, because obviously it is in the motion, and it comes to the rest, then only it will change its direction. Almost comes to the rest. So what we assume that at this position, kinetic energy is equal to the potential energy of that particular alpha particle. So for that, we write that kinetic energy is equal to potential energy. We calculate the charges half mv square, and the potential energy K Q1 Q2. This is electrostatic formula K Q1 Q2 upon R square. R naught. Potential. This is basically trying to find out potential. So electric potential is nothing but that electric potential is stored in the form of potential energy. So K Q1 Q2 by R naught, whatever is the distance between this particular to where. So this is what we are trying to calculate, the distance R naught. So R naught is basically given by K 2ZE square half mv square. So this is distance of closest approach. What is distance of closest approach? Maximum that distance, that minimum distance where it can reach up to nearer to the nucleus at alpha particle. Okay. Now this is Bohr's atomic model. Now Bohr's atomic model says what we have studied. this is basically it carried out everything whatever was explained by Rutherford, explaining what he said, that electrons, they revolve around the circular orbit. It was said by Rutherford also, and they revolve around following this particular thing, that their angular momentum is equal to nh by 2 pi. He also said is what electrons can revolve only in their discrete circular orbit. Discrete, that's why we are taking n values 1, 2, 3, 4 like this. We don't have anything in fraction. So that's why we say that discrete circular orbit, which is also known as stationary energy cells or labels. In electron in such a cell is characterized by definite energy, angular momentum, and orbit number. Orbit number means n value will be there, MVR value will be there, and this they'll have an energy for this, which is known as En. We'll see and how to calculate En further slides. While an electron is in this orbit, it does not radiate energy, although it is accelerated. So it will be, if it is moving in the prescribed shell. So, okay, if an electron is moving in the prescribed cell, if say there is an electron movement here, so this electron don't have to do anything. It will not lose energy if it is keep on revolving in this particular shell. If there's an electron which is revolving here, it is revolving in this, no problem. If this electron wants to fall here, or this electron wants to jump here, so to fall here, it needs to lose energy. It will lose energy, and if it wants to go up, this time it have to gain energy, because it is trying to do what? It is trying to either it is trying to come from N2 to N1. It can come from N3 to N2. So from higher, if you're coming lower, you have to lose energy, and if you're going from lower to higher, you're supposed to gain energy. So that is what he explained, which was not explained by Rutherford. Okay. For this and all, he had various calculations done. Okay. The calculations are same thing. Here again, kinetic energy and potential. So here what is there? This potential energy, the support is provided by which one? This is centripetal force. Because here there is for electron motion is there, so the centripetal force is helping that Coulombic force, electrostatic force. Using this, we are trying to calculate the formulas for these things. For using these formulas only, mv square. From here, I'm trying to calculate the velocity Vn. Angular momentum is what you are supposed to know is this is what is it? This is the final value, which is 2.2. 2.18 also many book write it as, but 2.2 is easy to remember. So I 2.2 into 10 raised to 6. Many book write it as 2.18 into 10 raised to 6. Okay, whichever you have remembered till now, that is what is useful for you. Okay. Next other values is the radius value, energy value. You can see the radius value is this one, n square. What you have to remember in this thing, few things which can help you in this is that you should know that nth orbit is proportional to n square. Like you were talking about energy. So energy, if you can see that this is kinetic energy, this is what is the equation. Potential energy, this is the equation. You can see that potential energy is basically 2 times of kinetic energy. If I'm talking about in terms of sign also, in terms of magnitude, you can just say it as 2K. Also, when I'm talking about potential energy, also there's a relation. E naught, R naught value is this thing, 0.5. This is for the first orbit, very first orbit. There's no jump. E naught is minus 13.6 electron volt. Okay, so say if I'm writing out E1, I can directly write it as minus 13.6 electron volt upon n square. So E1, so 1 square. E2, so it will basically become 13.64. So this and all you are supposed to use the formulas when we are solving the questions. Time period formula, you can see that time is directly proportional to NQ, inversely proportional to Z square. Frequency, magnetic field though is not that much important. Formula wise, magnetic field in very difficult situation questions that you can ask magnetic field. Wavelength of a photon 1 by lambda. This bar is known as wave number. This is known as wave number. RH stands for Rydberg constant. You have the values over here. Okay. This is energy label diagram for hydrogen. You remember it. It's just if you remember, see how we calculated this is basically minus 13.6 upon 1 square. This is calculated as minus 13.6 2 square. This is calculated as minus 13.6 3 square. This is calculated like this. It is 4 square 5 square. Where N values are given to you. This is for hydrogen atom or hydrogen-like atom. Hydrogen-like species will be basically what? Helium is there. Helium, if I'm taking what, 1 electron. From lithium, I'm trying to take 2 electrons. From beryllium, I'm trying to take 3 electrons. All these things will give me what? This all will be equivalent to H. Okay. So this is basically true for hydrogen atom or hydrogen type atoms. In case, in this basically when I'm talking about this thing, this is precisely only for hydrogen, the values. But this all formulas can be used for hydrogen, for wavelength you say, or for energy you say, all that can be used for hydrogen or hydrogen type, because we have an provision of adding Z in that. We can change the value of Z, which is atomic number. Okay, so this is tabulated thing. You don't have to know this. Just to explain that electron jumping. So Lyman series starts from 1, it goes till 2, 3, 4. Balmer 2 starts from 2, 3, 4 is the N2. Martian is 3, 4, 5 again. Bracket starts from 4. Puffin starts from 6. Humphrey starts. Puffin starts from 5. Humphrey starts from 6. So you don't have to remember the total values, but it's good to remember this two table, this thing. If you know this, you know that N2 will be 1 plus to that. Lyman, you need to know this. This is ultraviolet, which lies in your visible region as your Balmer series. Infrared is later. Okay. So you can remember it in your situation. Okay. So infrared is where I used to remember it as URAS, since I used to like UV. So UV radiation. So I used to remember that, yeah. U is ultraviolet, V is visible, and R is infrared. Everything stands for infrared. So R, I took it as infrared. Okay. Wavelength formula, momentum formula. There's a drawback of Bohr's theory. Any spectral line of hydrogen atom is not single. It will have several lines. It could not explain the spectra for those lines. The structure of multi-electrons atoms could not be explained. You can only explain about hydrogen or hydrogen-like species. No explanation was given using the principles of quantization of angular momentum. We didn't use anything which is related to MVR and H5. We could not explain Zeeman effect. Okay, it's a Zeeman effect and Stark effect also it could not explain. Zeeman effect talk about magnetic field and Stark effect talks about your electric field. So this all was not explained. Drawbacks and all will not be cannot be asked. Though they can ask you that which and this could not was explained by Bohr. Talking about nuclei, we know all this, that no mass of neutron is this much, mass of proton is this much, one atomic mass is written as this much. Atom represents mass number, Z represents atomic number. Isotones are having same number of neutrons but different atomic number. Isobar is same mass numbers but different atomic number. When you have isotopes, we know all this. Okay. Nuclear force, that's just to explain, this is what is there, this is theory, which is you can read this. The nuclear force is what it is bounded by basically the nuclear charges. There will be, you have electron proton which will have an important this thing in that they'll be holding each other with, and that's why we say that this is a very strong force when we are talking about nuclear force, because here they'll have a repulsive force, though this is so strongly packed. Okay. It's a very strong force. Nuclear fission, breaking down into two. Then you have fusion, when you have join it, nuclear reactor. These are all questions is not that much important when you come to these things. Although you have been summarized with whatever happens in the nuclear reactor and then what is nuclear fusion when we talk about sources of energy. When we basically nuclear fusion happens in sun. Junction transistor, basically I can have P and P, that is again positive, negative, positive, or I can have NPN, so negative, positive, and negative. So normally PNP forms emitter-based collector. Okay, we can have two things. We have common base and common emitter thing, which we'll see now. Okay. So when EV junction is forward bias, CV junction is reverse bias, and this transistor is known as active state. When both EB is which one, emitter and base, CB is what, collector and base junction are reverse bias, that time a transistor is known as cutoff state. Okay. Transistor is used in active state, which is CB and EB junction is forward bias. That time it is used in active state, which is amplifier. Current in emitter is equal to current in base plus current in collector. Common base amplifier. We have input alternating current AC source. VI is equal to VI sine omega t. This is V naught. This is input and this is output. So okay, this is amplifying it. Amplifying, you can see there is some height increment in this. This and all explanation part is not needed for your competitive exam. Formula wise, you are supposed to know this. Input and output are in the same phase. There will be no phase difference. Only there will be increase in the amplitude. DC current gain is alpha, IC by IE, current in collector by current in emitter. Resistance gain is RL by RI, what you took in that resistance, and this is input, this is output resistance. Power gain is again AV, which is virtual, and alpha AC. Alpha AC basically, we are trying to find out the current gain in AC. So AC current is find out by change in collector current by change in emitter. This is for common base. AC voltage gain is basically delta V naught is output by input. This is common emitter. Like common emitter also, you can say there is a phase difference. You can have omega t plus phi. In that you don't have phase difference. So there is a phase reversal of 180 degree. Beta, that is in that case it was alpha. Beta is IC by IB. AC current here is IC by IB. AV V naught by VI. AC current gain is beta AC into AB. That is maximum in CE mode. This is again RG resistance gain, RL by RI. RI is input resistance. 1 by alpha, again alpha is in which case? Alpha is basically common base. Beta is in common emitter. Alpha will be greater than 1. Beta will be, this is what will be the value. This will be basically, it will be greater than, alpha will be less than 1, and beta will be greater than 1. Okay. So this is basic theory for this thing. Okay, this is questions. Question wise, this is having good set of questions. I suggest you to try once. If you're not able to solve it anyway, I'll solve it. Meanwhile, because you all have studied for 2 years, some formulas obviously you'll be knowing. Question wise, these all are good questions. Let's try to solve the questions. If you're not able to solve, I'll solve it. Yeah, I have a good number of questions for this. Modern physics, this is very good. Please try. This is the first question. We'll try to solve the questions. If you have good theory knowledge also, you'll be able to solve this, or you'll be able to understand it at least when I'm trying to solve it. Okay, so please try. It's not hard. It's not hard. And the numbers which you can see here is like I have taken it from exam, previous year exams. Okay. You can check it. So it's a previous year exam question, and this is not very old. It is 2020, so it's last year's. Please try to solve. Not I'll solve it anyway. See that what is given in the question. You have a doubly ionized helium ion, okay. Proton and electrons are there. They're having same kinetic energy. See, if they're saying same kinetic energy and the relation between their respective de Broglie wavelength, I need to get something which relates de Broglie and kinetic energy. If you remember, we did the formula just now. Lambda is equal to h by mv. I can write mv as root over 2m kinetic energy. Now, because they're saying that kinetic energy is constant, same. H is a constant, it will not change. I have an answer. C. Yeah, C is right. Because why it will be right? Good. Why it will be right? So,
So
case why? Yes.
because the lambda is inversely proportional to mass if root under mass if kinetic energy is same.
Correct. Good. So if I have mass in this, so I have to just see the mass of whichever is more. Now mass of which will be more, it will be ulta of that. So whose mass will be more, lambda for that will be less. So mass of electron is less compared to proton compared to helium. So if I'm trying to write the mass will be having in this order, He plus helium, then I'll have a mass of proton and then I'll have mass of electron. So lambda will be ulta of this. So lambda will be electron highest, then I'll have proton, and then I'll have helium. Okay, so we'll move to next. No doubt with this. Let's go to the next one. Yeah. Assuming the nitrogen molecule is moving with RMS velocity. If you remember, I'll just give you the formula for VRMS is what? VRMS can be written in the form of root over 3 kT by M. 3 kT, where K is the Boltzmann constant. K is the Boltzmann constant. So one, obviously I have to see, one is what? RMS velocity, other is de Broglie wavelength. So de Broglie wavelength we are writing from that time, and so de Broglie wavelength we'll try to keep it in the form of VRMS is given to you, right? So we'll try to convert it into terms of kinetic energy so that I can use the velocity. So I have root over 2m half mv square. So half mvrms square. You can do this. By 2 can get cancelled. I have m square and v square. Correct. I have mv square. So VRMS is there. What I can write here is h root over m, and I have VRMS, which is in the terms of square. So root, so it will get cancelled. I'll get basically 3 kT because 1m and 1m will get cancelled. So I'll get 3 kT, 3 by 2 kT over here. The 2 will not come. So I'll get basically h over 3m kT. Now we can substitute the values. 6.63 into 10 to the minus 34. What is the given value here? And this is root over 3 times mass. We have to talk about nitrogen. So mass of nitrogen, if I'm trying to put what mass I put, 4.64 to 10 raised to minus 26. Then we have 1.38 into 10 raised to minus 23 Boltzmann constant, and I have 400 kelvins. I don't have to change anything. Let's put 10 raised to minus 42. Okay. This is 0.63 10 raised to minus 50. Yeah, so everything is fine. This is what to do. 2 will get cancelled here. VRMS value from here we substituted, which gives it this. So this is what is the formula in this case to find out the lambda. So I can find out the de Broglie wavelength using this. Answer will come somewhere here. Hope it is clear. Okay. Yeah. Next question. You can skip this. You can solve this one. can see that I can write the mass of the particle in this form, h by lambda v, using the de Broglie wavelength. Okay, I have two situations, so I can take it as m, and another one I can take it as m dash. So m dash I can take it as h lambda dash and v dash. So if I have to find out the particle is moving 5 times as fast as an electron, the ratio of de Broglie wavelength of particle to that of electron I have to find out. So I assume that this is what is the for electron. So if I'm writing the ratio for, if I'm trying to find out m dash by n, so m dash by m will be basically what? Lambda v upon lambda dash by v dash, which is the ratios. The particle is moving 5 times as fast as an electron. So basically the ratio is 1 by 5 I can write here. And the wavelength of the de Broglie wavelength of particle to that of the this thing ratio v to v dash, it's given to me as, so I can write it as this. So to find out the mass of particle. Okay. So mass of the particle is basically m. So if I'm trying to solve this, I have to write m 1 by 5. It's that's your assumption which you have taken it as electron, which you can just see that what is the ratio what they have given a de Broglie wavelength of a particle to that of electron. So particle to that of electron was given to, okay, this is electron and this was a particle. So particle upon electron. So I have used this thing. You can find out the formula for this, like the answer for this. The answer comes around something around. To solve it, you'll get it. Okay, next. Particle moving with kind of. So, Doctor says it is C. Okay, good. Let's see. The thing what we have is lambda is basically h upon 2m k root 2m k kinetic energy. Now this is one equation. It's according to the second situation, what they're telling is that when it became lambda by 2, that time the kinetic energy became 2m, kinetic energy became ke plus delta E. This is second situation. Now, if I'm trying to find out ratio of this, trying to find out ratio of those things. So I'll basically get what lambda upon 2 will be equal to root over kinetic energy plus delta energy over kinetic energy. This is what basically I'll have. I can square both the sides, so this lambda lambda will get cancelled and I'll get it as 4. 4 is equal to Ke. Komal also got it as C. Good. So delta E upon Ke. Basically, I'm writing it as that delta E will become 3Ke. So basically, so good. Next. Yeah. That's all this. Okay. So see, because it's an inelastic collision, now you say that they're telling it on the right angle. So say if one is like this, other have to be like this. So there, so this is moving with the lambda 1, say, and this is lambda 2. Then the resultant is angle between them is 90 degree. So they'll have some result. It can go in direction. I'm assuming that to be here. So now if I'm trying to find out the P final in terms of vector addition. So vector addition basically how we find out resultant of two vector. Write it as p1 square and p2 square. Why I'm not writing the further term of 2p1 because 2p1 and p2 cos theta cos 90 degrees 0. So we're not writing that term. How much will be PF? So PF will be basically given by the potential final highlighted as h by lambda because lambda is equal to h by mv. Mv is potential. For p1 square it will be h square upon lambda 1 square. For this it will be h2 lambda 2 square. So if you take h will come out from here and this will basically cancel the term. So I'll get 1 by lambda is equal to 1 by lambda 1 square plus 1 by lambda 2 square solve this out this. Okay, so it's just like it is using some concepts of vector over here. So they have moved the two particles move at right angle to each other. Okay, so that's why we are using cos 90 degree. Okay, next. Particle of mass m, charge q is accelerated by a potential difference of 50 volt. 50 V. Okay. Another particle b of mass 4m, charge 2500 volts. Both 50 and 2500 volts. Charge q is accelerated of both are q. Ratio of lambda and lambda b. Okay, so see, just now when we started the class, I said you the charged particle is moving with a potential V. We write the energy for that is equal to QV. Okay, so this QV is there, this charge. So I can write the lambda in this form, that lambda is equal to, it can be written in the form of H by mV or H by mk. Instead of kinetic energy, I can write it also in this form because energy is equivalent to this thing. So 2mqv. Okay. After this, if this is done, everything else is done because now we have to find out the ratio of lambda a to lambda b. So lambda a upon lambda b. Lambda a upon lambda b, because it's inversely proportional, h and h gets cancelled. So and 2 also we don't have to include, though if you want you can. Okay, so 2m. Autumn says it as C. Autumn says it as C. Okay, yeah, correct. C is right answer. So 2m is there, 2mb, I have to write qb and vb upon, again I have what? I have 2ma, qa and va. Okay, so I have root, so I can find out the particles of mass m and charge this thing. Okay, and I have another is 4m. So basically I have, if I solve this thing, I'll get rid of what? 4m, 2 gets cancelled, root 2, and side 2 if I'm talking. So total 4m, q is there, volt is 200,500, and here we have what? mq into 50. This gets cancelled, this also gets cancelled. So somewhere around, you get it as, this will be what? This will be 2 under root how much? So 50. So yeah, 50. Okay. So 49 is 7. So it has to be more than that. To the next question. the protein wavelength. Do this. Okay, try this. This is basically we will be using concept of one chapter, other chapter, everything will be mixed. Not be direct, like all of them will be not direct. To solve this, okay. Solve this. This is not that hard. Only one single concept and you have the answer. You can try. It's a read-only wavelength. Okay. Atom says is A. Further, I want the ratio of velocity of proton and the alpha particles. Proton and alpha particle, if they mention, you need to have proton on the top and yeah, so 4:1. That's what I was saying, Gautam. You need to have a Como says C, correct? Yeah, Gautam, correct. Yes. That's what you have to be. If they mention the proton and the alpha particle, so they basically want proton to be on the numerator and the alpha particle to be on the denominator. So good. Okay. So the next one. Elastic. Yeah, we can solve this. It's a head-on collision and elastic. Energy and velocity stays constant. Let's solve this. say a particle of mass m. What all is mentioned here is mass m is there. So I have a mass of a body ma, which is m, and I have mass mb, which is m by 2, and we have the initial velocity. I assume that here initial velocity for a was something, I'll assume say v, and for b the initial velocity was 0. Why I'm doing all this? Because I have mentioned it's an elastic collision, so I need to find out initial and final concept I'm supposed to use. Assuming that final velocity for this will become say v1, and final velocity for this becomes, assuming it to be v2. So I have answer. Bottom says it as 3. Okay, I check it once. So if I'm doing this thing as a rest, the ratio of the de Broglie wavelength of lambda to lambda. So now, so if I'm trying to use the collision concept using conservation of momentum, initial momentum will be only this much m, whatever of the, for one body we don't have, only for the first body we have. So I can write it as final initial momentum is equal to final momentum. So I have mv1 plus m by 2 v2 by v2. This is if I'm using this, and so when this mm and mm is cancelled, so I have v is equal to v1 plus v2 by 2. I have another answer. Both are after collision, then half half. Okay, so this is this is where I'm trying to find out the which both are after collision, then half. No, this is when I'm trying. This is not after collision. Before final, they are elastic collision. They will not be half and half. Why will become half and half? It's an elastic head-on collision. Elastic means there will be no loss. There is no kinetic change. There will be no momentum change. So basically, I have anything, any other values given over here. The ratio of V1 if anything is there. So I have 2 V1, V2. This is U1. So I'll just keep it in this fashion. So we have what? 2 V1 plus V2. What are this thing? And then this is there one. Then according to the law of collision, what we can do, coefficient of restitution is given as V2 minus V1, U2 minus U1. So I have U1 as 0. So I'll just write it as U. Another term is 0 for me. So I'll get from here U value is equal to V2 minus V1. Okay. So if I'm trying to solve the equation 1, 2, we'll get it in the terms of this. So I think his answer is right. Okay, and even if I have the answer, so this bottom is right. Okay. Will be de Broglie wavelength accelerated by voltage this much. This is easy. Skip this. This is easy. Yeah, solve this. So it's easy on this one. Difference. Yes. D. This is direct relation. So there's no discussion. There is no problem with this. Answer is D. Good. Formation of covalent bond is basically, it's like none of these because it's basically explained in the terms of we say that as molecular orbital theory. here we need an equation which is Bragg equation, that is lambda is equal to 2d sine theta. Basically what happens is we have two surface over here. So if there is a light which is falling on this, and then this is like this, so this will be basically in the same place. This is what is theta over here, where there's scattering angle, and this distance is basically small d. So 2d sine theta. I have given you, this thing is given, a beam of electrons or P scatters from a target having atomic spacing of 1 angstrom. So the atomic spacing is given to you. This atomic spacing is d. D is atomic spacing. The first maximum intensity after that 60 theta, 60 degrees. Then you have to find out electron volt. Lambda value of this. How we'll find out E? We know the formula. We have another lambda value as what? Root over 2m kinetic energy. Like this. Include both of this. We have all the values to find out E. And E we have to find out in electron volt. So this will give you the answers and convert it also. Only thing what we have to convert here will be what? The mass is there. Solve this one as we get 2 into d. D is 10 raised to minus 10, converting it into meter. And then sine theta is root 3 by 2. Root 3. So I solve this is gets cancelled. I take basically root 3 into 10 raised to minus 10. So root 3 into 10 raised to minus 10 equals to root over 2m ek. If I square this side as well, so it will be 3 into 10 raised to minus 20 equals to 2 into 9.1 into 10 raised to minus 31. Okay, because I have to convert it into electron volt, so I need to multiply it in joules, has to be converted into electron volt. I should divide this. Should be divided because I have to convert it into distance. In here, I've done a mistake here. I didn't write the lambda is equal to h by 2. This is how it is. So, what d value we have got, root 3 into 10 raised to 3 into 10 raised to minus 20 is equal to h by h square by 2. M is 9.1 into 10 raised to minus 31. Now I need to then kinetic energy here. Need to find out kinetic energy. So it will be h square, so 6.62 into 10 raised to minus 34 whole square upon 3 into 10 raised to minus 20 into 2 into 9.1 to 10 raised to minus 31. Because we want answer in electron volt, so I have to multiply it there. This will give you the answer. In this answer, we get something around 50 electron volt. So see, this is I'm trying to give you the possible combinations of formulas which can be used in the modern physics. I can interrelate something. There is nowhere you see one where place we are using the accelerated charge particle, one where you are using this thing, one where you are using the Bragg's equation. So you can have anything getting connected to any other place. So you need to know all the formulas and which is coming to modern physics. It is a very scoring thing. It's not like it's a very difficult thing, it's a very scoring part. Let's solve this. Need to find out work function. What we have is kinetic energy is equal to work function. We represent it as phi naught. Okay. And sorry, not kinetic energy here, right? We'll have here the energy of photon. So we have psi over here and this plus kinetic energy. Surface of metal is illuminated alternately with photons of energy. E1 is 4 electron volt and E2 is 2. The ratio of maximum speeds of the photoelectrons emitted in this case is 2. Work function of the metal. Okay, work function of one particular metal does not change again and again. Okay, so what I can write this equation in form of kinetic energy. If I want to write, I can write it. Okay, Gautam says it as 3. So then check once. I have an answer which says 2. Gautam answers 2. Okay, so answer is coming as 2, though we can solve it. Kinetic energy is equal to phi minus phi naught. This is a good question. Now, what is kinetic energy? I can take the kinetic energy ratio as half mv1 square upon half, because mass is not changing, half v2 square. And I can write it as 4 minus, for the first case, 4 minus phi naught as the function, And for the second case, 2.5 minus 5 naught. I can cancel this 2. And the ratio of maximum speed of the photoelectrons emitted in two cases is 1 by 2. So 2, that is given as 2. So ratio of 2, so square, 2 square, 4 minus 5 naught, and 2.5 minus 5 naught. So this will be basically 4 into 2.5, that is 10 minus 4 5 naught, which is equal to 4 minus 5 naught. This gives me basically 5 naught, that is work function equals to 2 electron volt. Because basic questions only, not like very difficult. And this is very recent. You can see this. Next. Okay. It's the slope between V stopping potential and to find out minimum energy for rejection of electron. Minimum energy they say, or they say your work function. Basically, they're talking about the same stuff. See, this graph, the slope of this gives you always V by A is given. So you can write the stopping potential, we can write it as HV, okay, work function. Or I can write it as, this will be in terms of joule. Okay, without telling you, I can just divide them by E to convert it into electron volt. Now you need to find out the value of phi. So H is 6.62 into 10 raised to minus 34. Now V is how much? V is equal to, this is the point. So 5.5 into 10 raised to minus 10 raised to plus 40. So 1.6 into 10 raised to minus 90. This gives you answer somewhere nearer to 2.27 electron volt. Okay, so this. the data given, this basically what they're saying is 3 times of ratio of 3 times of K max upon K maximum, 2 cases is equal to HC by 200. Okay. Lambda HC by 200 minus work function. Okay. Upon HC by 500 minus 5. This 5 is right. 5 you write or 5 not you write work function. This is 5 not will be multiple. This will be basically, yeah, we'll get it in this sum. It's HC 500 minus 5 naught on this being multiplied to 3 equals to HC by 200 minus 5 naught. HC value, if I'm talking about, we try find. If you have read it, it is many people take it as 1240 exactly, but author have an answer 0.61 electron volt. Okay, right. 0.6. So this will be basically equal to this value is basically you can solve it. It is we take this values. Many people take it as 1240. Exact value for this is 137.5. Okay, so you solve this. So this gives you 5 value as 0.61 electron. Next. Thus, Yeah, photons, right. Okay, so how the thing is solved here is I can see that number of photons will be taken as they're asking me the ratio of number of density of photons of X-ray to the number density of photons of visible light. So that is given by formula for that is power upon energy. Energy for photon I can write it in terms of Hc by lambda, because lambda is given to me. So now it's clearly you can see that n is proportional to lambda. So I can see write it as what n1 upon n2 will be equal to lambda 1 upon lambda 2. Lambda 1 is basically both is a nanometer. This is in this and this. It's all this. So first thing what we should check is the photon which is falling on this, it is enough for the ejection or not. To do that, what we'll do, I know that this C they have written HC is 1240 you take. So 1240 lambda given is 310 nanometer. 310 nanometer. This gives you the energy in the terms of 4-electron volt. Now you can see that 4-electron volt is greater than 2-electron volt. So obviously ejection will happen. That's the first thing you're supposed to check. Okay, check. Now what we'll do is we'll convert this into joules. So now 4-electron volt, to convert it into joules, now what I'll do, I'll multiply it in the terms of 10 raised to 19. Because this is given in the terms of watts per centimeter square, so you know that watt is basically, it will contain this is intensity unit. Okay, so 4 into 10 raised to minus 19. This is in terms of joule. This will be basically 6.4 into 10 raised to minus 19 joules. As the question says, to find out a number, what I'll do is I can divide this, what intensity is, the beam of intensity is this much. So this intensity is divided, this intensity multiplied to 1 electron have this much. Okay, is divided by the total energy what we got it here. This is 6.4 into 10 raised to minus 19. If you find out the ratio, this many total number is there. Now to find out photoelectrons emitted per second, what we'll do is if I divide 10 raised to 14 by 10 raised to 3, which is because they have mentioned if 1 in 10 raised to 3 photons ejects an electron. So out of this total number of photons, this many are ejecting an electron. So this will be basically equal to 10 raised to 11. So this is what we will answer. This will be what the value for x will become 11. On this. So when we are trying to solve this question, it's basically we are trying to find out K maximum is given to us. So K maximum is basically I need to find out K maximum. I can write K maximum using this formula H nu minus H nu minus H nu naught. Okay, if I'm doing this, I can write H nu as Hc lambda minus Hc lambda naught, where Hc can be taken common. 1 by lambda minus 1 by lambda naught. These values are given to you, which is 1 by 260 minus 1 by 380. So this comes up there, so taking it as 0.31240. Take it as 1237 also, it's average. There will not be much fluctuation. In general, the value is 1237.5, so 1237. Here it will become 120.380 into 260. This gives answer something around 1.5 out of 10. So, next one. So if you try to solve this, the question can be written in the form of n, which is number of emitted per second. I can write it as power into time into lambda upon Hc, on to time into Hc. The power value is given to us 2 megawatt, that is 2 milliwatt, that is 10 to minus 3. Time is 1 second. Time is 1 second. and the lambda is given as 500 Newton. So 500 nanometer is 10⁻⁹. Okay, then H is there, HC value. Often says is A. Yeah, A is the right answer after substituting the value 6.6 into 10⁻34, and C is 3 into 10⁸8. 10+8. So this will be the answer. So this will give you the answer for this. Right. Next. Yeah, solve this. Solve this. Okay, so formula for this, the intensity formula is written as ME over area into time. Area is given to you, intensity is given, work function is given, the energy of the incident photon is 10 electron volt, and only 10% of photon produces the electrons. So we can substitute the formulas in this to find out the answer. 16 in milli is there, so we can write it as 16 into 10⁻³ n by t. Area is given, so n by t, I have to find out the number of electrons per second, so n by t will keep it like this, and E, I can write it as 10 into 1.6 into 10⁻⁹, 10 electron volt, I converted it to joule, area is given, that is 1 into 10 raised to minus 4. You can write it as minus 4 as well. So solving this, we get n by t value as, okay, so n by t value will be some 10 raised to or 12, but they're saying only 10% of it produces the photoelectrons. 10% of this number will be equal to how much? 10 raised to 11. This is another new formula for you. We're just trying to interrelate the formulas. Maybe the next one. So this.
This is half question only.
Okay. So look at this. You solve the question number 2 here in the line spectra of nitrogen, not the first one. This is next from here. Okay, so for if I want to write according to the Bohr's formula, I have 1 by lambda is equal to Rydberg constant 1 by n1 square minus 1 by n2 square. For Lyman series, if I want to write, the lambda minimum will be given by when there will be least transition. So that time it will be this total value will basically become 1. So I'll get it equal to R. Because here what I'll take is as the n2 will be infinity here. So this term will become 0 and n1 will be 1. So if I have that R1 into 1, that is R. And if I'm trying, this is for Lyman. We are writing this for Lyman. And if I'm trying to find out lambda maximum over here, lambda maximum will be given as R. So the first transition where n2 value will be 2. So 1 minus 1 by 4. This will give you the values 3R by 4. This is for Lyman. So I'm trying to find it for Paschen series. So for Paschen series, if I want to find it as, so lambda minimum will be equal to R 1 by 9. Okay, here because after Lyman is Balmer, after Balmer we have Paschen. So in that case, the n1 will be here. N1 will be basically 3, but n2 will be equal to infinity again. Again, if I'm trying to find out lambda maximum, so lambda maximum will be equal to 1 by R into 1 by 9 minus 1 by 16 because 3 to 4. So this will give me the answer as in the terms of 7R 16 in times 9. 6338.4. So the corresponding difference for the Paschen series. So if I have the difference for this one, if I want to find for lambda maximum and lambda minimum, it will be how much? Lambda maximum, lambda minimum in this case will be equal to 4R by 3 minus R. So yoga is minus 1 upon 16. So lambda max minus lambda minimum in this case will be 304 basically after substituting the Rydberg constant. Here it is this much. So if I'm trying to find out lambda maximum minus lambda minimum, so lambda maximum lambda minimum here should be lambda maximum lambda minimum. It will give you 16 into R upon 7R minus 9 by R, which is nothing but equal to 81 upon 7R. Okay, this is a difference. So if I'm trying to find it corresponding to this thing, okay. So 81 by 7R. So basically I'll have 81 by 7R. This is substitute to find out the answer. This will not give you negative thing. I'm sure. Okay. So what you have to do for that value? We try this. Try the second one. This one. This is second. Let's have 3 questions. This is second one. This is third one. Try second and third. Try second and third. For the second one, if I want to solve, I can write it as, because 1 by lambda, it is 9 times of Rydberg, so 9R from the excited state to the ground state. So excited state to the ground state. So 1 minus 1 by 9, second excited state. So if I solve this, this is basically, this will give me the value as lambda is equal to 1 by 8R. So if I'm taking Rydberg constant as 1.097371, whichever values you remember, that is fine. It's no problem. So solving this, you'll get the answer for lambda is 11.39 nanometer, approximately equal to 11.4 for the second one. For the third one, if you solve, the answer is somewhere, this is for the first member of Balmer series. So the wavelength of the second member you have to find out. For the first one, you can find out taking 2, 3. For the first series, it will be what, 2 and 3, because Balmer starts from 2, 3. So when I'm talking about the second member, so it will be 3, 4. Here it will become 3, 4. When you solve this, so this is 3 values for what? This is N1 and this is N2. And this is value for again N1 and N2. So this gives you finally the value as 486 nanometers. To solve this. Okay. So you have to keep on solving more and more questions so that you get your more perfections while solving the questions. Okay. So just for the today's class. Thank you for joining. Okay.
Thank you, sir.